Okay, so for this video, we'll be going to apply the theory knowledge that we learnt in part 1. And where we left off last time was recognizing that when we are dealing with larger objects such as the Earth and the Moon, this R in the gravitation formula is equal to the distance between the two objects. So in this case, the distance between the Earth and the Moon plus the radius of the Earth plus the radius of the Moon. Right? So that's the radius of the Earth, and that's the radius of the Moon, right there. And that comes from the fact that in our definition, the force is inversely proportional to the square of the distance between the center of mass of m1 and m2. So for the first problem, if you remember, Elon Musk put a Tesla in space. So there is a Tesla 300 kilometers above Earth surface. So for this question, I would like us to calculate the velocity of the car. Also calculate the period, and also calc the angular frequency. So if we draw out the scenario, we have Earth right here, and we have the little car, let's draw it as a rectangle, and it's moving in orbit around the Earth. Now, this is circular motion, and therefore there must be a centripetal force. We know from the previous video that this centripetal force is going to be provided by the gravitational force. So that means Fc is equal to Fg. We know that Fc is mv squared all over r, and our gravitation is g, big M, little m, all over r squared. And so using this knowledge, we can complete our part A. If we take this equation, and we can redraw it down here, we can see that we can cancel out these two m's on both sides, and we can also cancel out this r with this power. And what we get is v squared is equal to g m all over r. And therefore our velocity is equal to the square root of g m over r. And so plugging in our numbers, we can find the velocity of the car. So g is 6.67 times 10 to the negative 11. Our mass is the mass of the Earth. We know that's 5.97 times 10 to the 24. That's from the previous video. And we also know our radius is 6370 plus 300 times 10 to the 3 squared. The reason for that is because 6,370 is the radius of the Earth in kilometers, plus 300 kilometers, and then obviously to put it into meters, we need a times 10 to the 3. And this gives us a velocity of 7,727 meters per second. There we go. Now something to note, if we look at this equation here, you can see that the mass of the actual car itself is not taken into account. Only the gravitational constant, the mass of the Earth, and the altitude plus the radius of the Earth, that's our r, so the distance between the two center of masses. So the mass of the car is not taken into account. And what that means is that this speed is the speed of any object at that altitude. So at an altitude of 300 kilometers, every object goes at that speed. So now moving on to part B, the orbital period, we know that velocity is equal to distance over time, and therefore time is equal to distance over velocity. Now if we take our situation again, we have our Earth and we have our car. We can see it moves in a circle like so. And so the total distance covered is the circumference of a circle, which is equal to 2 pi r. The r in this case is our radius of the Earth, which we know is 6370, and this distance here is our 300 kilometers as well. So in total, that r is equal to 6670 kilometers. There we go. And the velocity traveled is the velocity that we found previously. So the period is equal to 2 pi times 6670 times 10 to the 3, all over our velocity, which is 7,727, and this gives us a time of 5,424 seconds, and that is equal to 90 minutes which is also 1.5 hours. Right. Now for part C, to find the angular frequency. Just a quick recap on what angular frequency is. If we have an object moving in a circle, again, like our car, in a certain period of time, it is going to move through a certain angle. Let's say this angle right here. We can call that angle phi. So in a certain period of time, it's going to move through a certain angle, and therefore we can define that as omega, which is the symbol for angular frequency, is equal to the change in the angle all over a certain period of time. And if you're familiar with the conversion from circular motion to linear motion, you can see that this looks oddly familiar to velocity is distance over time. And that's why angular frequency in circular motion is also described as angular velocity. So they're the same thing in circular motion. So that means if we take our situation again and we have our car and it's moving in an orbit around, we can see that the angle that the car moves through in a one rotation is equal to 2 pi radians, right? Because one whole circle is 2 pi. And the time taken is equal to the period. And so therefore our angular frequency is equal to 2 pi all over our period, which we found out before, which is 5,424 seconds. And therefore our angular frequency is 1.16 times 10 to the negative 3 radians per second. There we go. Okay, and now we're done. See, we've applied the gravitational law in a few different scenarios, and you should be good. Sweet.